Okay, well, good afternoon, everyone. Welcome to EECS151 to 51A, Introduction to Digital Design and Integrated Circuit. Today, we're going to have our 14th lecture of this semester. We're already halfway this semester. We're going to talk about delay and especially focusing on the using inverter as a really good example to understand what kind of factors that actually contribute to the delay of our circuit. So before we start, since we get to more hardware design part, it's also a good reminder to think about how we both structure this course and also later courses in thinking about hardware design and hardware prototyping. Some of you know, like we talk about the Berkeley courses structured, and we do have a tape out class coming up next spring, where throughout the class, throughout the semester, you will be able to actually tape out a very complex SoC with both digital circuit and also analog circuit there. And students with 151 to 51A background meet the prerequisite for that class. You are very well prepared to actually bring in your own module into the tape-out class. So structuring a tape-out class like this is always, in some sense, the dream of the instructor to actually bring the tape-out experience, bring the hardware design experience to the students, both senior undergrads and also junior graduate students. In fact, actually, in late 70s, one of the first actually, basically also a tape-out class was actually designed at MIT by Lin Conway. We mentioned the VLSI design book from Mead and Conway, where we talk about design rules and also significantly simplify the design rules in their introduction to the VLSI design there. And back then, late 70s and early 80s, Conway was also affiliated at MIT, and where she actually taught also similar to 151, or actually more similar to the tape-out class that will be introduced next semester, with a group of senior undergrads and also junior graduate students, where students work together throughout the semester. And at the end of the semester, they will actually bring in, put together their design onto the same chip and actually tape it out in the end. So if you go to actually this link, it has actually more complete history of how Conway actually designed the class and how she organized the students and also teaching staff together and also secure the tape out resource to actually really deliver the chip in the end. And you can actually see the different design here. There were actually, I guess, at least a handful, yeah, more than 15 teams here, and each team basically have their own individual module and then assemble them together. That become the final chip. So that's a really cool project that was pretty transformative in the sense to see fairly complex design using state-of-art design process was actually achieved by students actually. So a lot of time we say only experienced designers can actually do hardware design. It takes a lot of effort. It also takes a lot of time to learn that. But really, in terms of hardware design, you really need to learn by doing, right? So having this kind of tape-out class is really a good opportunity to actually learn more like hands-on design experience throughout the semester. So most of our classes, especially hardware classes, are structured in a way that's fairly project or lab heavy. You notice some of that in this class already, also in other classes, with a very special focus on thinking about not only just like the lectures and the homework, but really get your hand dirty and get into the design process. So 151 to 51A structured this way, and the tape-out class, if you're interested, and all of them already meet the prerequisite, will give you an experience to really get through the design process and build your own hardware, your own chip in the end. So stay tuned, and if you're interested, feel free to reach out the instructor of the tape-out class, and we are really excited to start doing that again. Well, after like this is more than almost 40 years, but to do this using state-of-art process again in an education setting. So exciting time. With that, let's get started. So a quick review of things that we covered this past Tuesday. We started talking about transistor. We covered the RTL level design, the Verilog, and also microarchitecture using RISC-V core as an example of both data path and control, and also pipelining logic. After that, we get to more lower level, the hardware circuit side, in really thinking about how we actually build and implement each individual module. So we covered FPGA briefly last time, and then we get to the CMOS module. We talk briefly about CMOS transistor. I'll do another review later. Some students reach out after the class mentioning a lot of the topics are a little bit far away from their comfort zone, which is okay. We do have like fairly diverse student background, have both CS and the EE students coming together. It's also a good opportunity actually to work together. So if this concept are a little bit far away from your comfort zone, it's okay. I'll do another review during today's lecture, and also we'll also cover that, also remind you and also help you exercise that in discussion and also homework. So at the very high level, we mentioned we can basically think of the MOS transistor as a switch, right? If we apply a voltage, if the voltage is actually greater than threshold voltage, the switch is on. For NMOS, if the voltage is actually less than the threshold voltage, the switch is off. And then we talk about some of the internals of the NMOS, not only just the on and off, but also the linear and also saturation region. That's basically our discussion on thinking about how current actually really change based on different voltage between the drain and the gate for both NMOS and the PMOS. After that, we also briefly talk about some more advanced fabrication techniques like both SOI and the FinFET. Those are really just for your understanding, just see, especially when you see the news these days, a lot of time we're talking about advanced technology and whether the fab actually are equipped or not equipped to further invest in this kind of technology. So some of the state-of-the-art technology, sometimes you see the names, but this discussion give you a little bit more context, at least what kind of the problem that they are trying to do. And then we get to the start from the transistor and then how we can actually assemble transistors to build CMOS gates. We started with the inverter and then get started on the pull up and pull down network. And in today's lecture, we'll continue the discussion further talking about how we can not only just build the inverter, but any logic using the CMOS pull up and pull down network. So with that, as I mentioned earlier, I will do another quick review of CMOS transistors and then get to our gates discussion. What are the different kinds of gates that we can build? And then we'll get to the inverter delay, why it matters, and what kind of parameters or what kind of physical attributes are actually associated or contribute to the delay. And then if we have time, we'll talk about the sizing of the inverters and to be prepared to talk about more general delay of more general gates and also sizing general gates next week. So just a quick review. I realized that maybe a lot of topic is like you learned in 61B, that's already your freshman year, so it has been a while. So just a quick review when we think about the electrical behaviors, right? So the first one, a very straightforward one, when we think about any electrical behavior, is basically the Ohm's law, right? So whenever we have a whenever we have a resistor, right? So the current that actually flowing through the resistor is basically linear with the voltage, right? You have a higher voltage, the current is higher. You have lower voltage, the current is lower. So when we talk about IV transfer characteristic, current voltage characteristics, that's basically see how current actually change with voltage. So you have a resistor, the resistance is actually fixed. So the current and voltage transfer characteristics basically a straight line. And the slope is basically our resistance. And it's basically this linear line here, you will have a higher voltage with a fixed resistance, will have a higher current. Sometimes the resistance, if the resistance is not fixed, we may have like variable resistors where we can actually change the resistance of our resistors. In that case, if we look at the current and the voltage behaviors, they may actually have different slope, right? The slope is basically associated with the resistance of the resistor. So this is basically, we talk about the current, how current actually change with voltage. Everything basically boils down to what's the resistance in between and how the current, given a particular resistance, how the current actually adapt with voltage. So a little bit more on resistance. So if we think about the physical resistors as a 3D structure, where you have the length of your resistors and also the width of your resistors and also the depth here, right? And your current is actually flowing through from like this way, like through the paper, like basically the highlighted region here. Right, so the current is actually flowing this way, right? So this is a cross section. So this is a region the current actually flow through. So we think about the resistance, what are the different factors that contribute to the resistance of the resistor here? So of course, there are the material here, different material have different resistance. We use this parameter rho to represent that. But we think about the structure of the resistor, right? We talk about the length and the width, right? So you think about the resistor here, if the length is longer, meaning we have a longer wire or have a longer resistance, that basically the resistance is longer, right? Or it's higher because the wire, you think about wire as a resistor, when the wire is longer, it actually needs to go through more material. So the overall resistance is higher. So it's actually linear with the length of the resistor. And another factor is basically the area here. Let's assume the depth is the same. Let's just focus on the width of our resistor, right? So if our resistor is wider, meaning that we can have more current actually flowing through our resistors. So that actually, so higher current, actually lower resistance. So our resistance is actually linear with the length of our resistor, but inverse proportional to the width of the resistors. So in CMOS technology, we'll see that a little bit later. Again, when we talk about the size of transistors, it's actually the same thing. Even in the context, we're talking about the transistors, but you can actually apply your understanding of the resistors there. We're basically trying to modulating the length and also the width of our capacitors, and fundamentally, basically the length and also the width of our resistors. So with that, by modulating the length and the width, that will also change the resistor behaviors or the transistor behaviors, actually the way we describe that. So that's basically a little bit more fundamental, just what are the context and what kind of electrical behaviors we are interested when we think about CMOS transistors. So a little bit more on the resistors here. So we talk about individual resistors. What about the resistors are actually connected together? So we can either connect them in serial or connect them in parallel, right? So in serial, when we have two resistors connected in serial, the overall resistance basically double, right? So it's similar, right? We have a longer length of our overall resistance here. So it's basically doubling the resistance. And then back to our current voltage characteristics, with a higher resistance, the slope is basically this one, because the resistor for a given voltage, the current is actually lower because we have a higher resistance. So we'll talk like later when we think about the CMOS technology, this is also equivalent to make the transistors longer or longer if we think about the length, or narrower if we think about the width here. So or what about we put two transistors in parallel? So here in this case we mentioned earlier, it's like make your transistors wider, right? So the total resistance, because you have actually two paths now. So the equivalent resistance of a parallel resistors is actually half of the individual resistors. And we'll actually we'll also see more actually when we talk about transistor sizing, how we can actually make wider transistors to actually have lower resistance, because it's like basically putting two things in parallel. So this is basically, we look at the current and voltage behaviors when we see actually different curve with different slope. That basically means we have different resistance actually exist in our hardware, in our circuit. Or in the CMOS example that we showed earlier, we also see the different line here representing different current and voltage characteristic. That basically means we have different resistances that actually being observed. So just a little bit more recap to get you more familiar with more like those electrical concepts there. And with that, just a little bit more review on the MOS transistor, our discussion here, and more tied to the basic electrical behaviors of resistance, current, and voltage. So we talk about this is a MOS transistor we introduced last time. We have 3 terminals and gate. A gate is controlling, well, basically remember the gate of our planar MOS transistors, and then we have a drain and the source, the other 2 terminals. And we mentioned that we can abstract our transistors as basically a switch, right? A switch with a resistor here. So when gate voltage is high, and this NMOS transistor, when gate voltage is high, our NMOS transistor is on, right? So we turn on our switch, so things are connected. If gate voltage is low, we actually turn off our NMOS transistor, so the switch is open, so this is not connected. Just one more thing here, when we say on and off, it's actually not say whether the gate voltage is actually greater than 0 or less than 0. It's actually related to the threshold voltage here. So if we look at whether the transistor is on or off, if it is actually less than the threshold voltage, the gate is not turned on, so we don't have a connected switch. So this is not connected. Our switch is off. And if our gate to source voltage is actually greater than the threshold voltage, we turn on our switch, so our drain and the source is connected. So if we look at the current and voltage characteristic here, the current flowing through from drain to source, and also the voltage between drain and the source, right? So what we mentioned earlier, if the gate voltage is actually less than threshold, the switch is actually not connected, so there's no current flowing through. So that's the first part. The off part, our switch is off when the gate voltage is actually less than the threshold voltage. What if the gate voltage is actually greater than threshold voltage? Let's say the gate voltage is at VDD, so it's the highest voltage in our circuit, so our switch is actually on, connected. So with that, so this is basically the picture we saw earlier, right? A resistor, and then the voltage, the VDS is basically the voltage between the 2 nodes, the 2 terminals of our resistor here, right? So this is basically what we discussed last time, the linear region. This is basically the same as the resistor circuit that we showed earlier. If you have a higher voltage applied to the 2 ends of the resistor, you have a higher current, right? So this is basically the linear behavior of the resistor that is actually proportional to the voltage. And the current is actually proportional to the voltage between the 2 terminals of our resistor. So that's what we mean by the linear region. Just one more region that we actually mentioned when we think about really a little bit more detailed CMOS behavior is that the gate to source voltage here, we also need to actually aware the differences between the gate to drain voltage also need to be greater than the threshold voltage. So basically, we increase the drain to source voltage as what we're doing here. We increase the current, but it's our drain voltage is actually too high that doesn't satisfy actually the gate to drain voltage is actually constant. After that, that's what's basically called saturation region. You can basically think like the channel is actually saturated. And then after that, no matter what the voltage actually you're applying between those 2 channels, you always have a fixed current. So this is basically our resistance or linear or resistor region. And after that, this becomes our saturation region. Basically, we always have a fixed current, no matter what is the voltage that we apply there. So this is basically the transistor behavior. 3 parts. The first part is if the transistor is off, the gate voltage is less than threshold voltage, nothing is on, no current. Right? The second part, if the gate voltage is actually greater than threshold voltage, we can actually turn on our switch and then being connected, and this just acts as a resistor. The relationship between current and voltage is just linear, right? Higher voltage, we get higher current. And then after that, if our voltage, drain and source voltage is too high, that basically get to our saturation region, where no matter how much actual voltage that we apply, the current basically stay at that region. So those are basically the 3 lines I drew explicitly here. So that's basically the current and the voltage characteristics that we discussed last time. One more thing here is, so far we only have 2 points, discussed 2 points about the gate voltage, right? So one is a gate voltage less than threshold, it is completely off. The second part is the gate voltage is actually basically the VDD, and we talk about the linear region and also the saturation region. There is also part, what if the gate voltage actually something in between? It's actually greater than threshold voltage, but actually less than the VDD. So with that, different gate voltage will basically have different curve there, right? Because we are plotting how the drain voltage, how the drain to source current actually change with the drain to source voltage. And then with different gate voltage, we basically have different curve here. Different gate voltage, you can basically think of this becomes a variable. Remember, we talked about the variable resistor part. With different gate voltage, what's being fundamentally changed is that instead of this fixed resistor, we make this resistor, the resistance of this resistor is actually related to the gate voltage here. So the different lines here, we also use the same symbol, like remember the variable resistor symbol here. So this is again our variable resistor. Basically with different gate voltage, we also have different resistance. Remember the slope is basically the resistance of the circuit or the MOS transistor here. So here we basically have different slope because we have different gate voltage here. So just a quick review, and we go through a lot more like the details. Sometimes it could be confusing, but at a very high level, basically, again, those three operation regions, we think about how current change with drain to source voltage with different, with the region here, and also notice the gate voltage can also change, and different gate voltage will basically have different line here, and then act as, if we focus on the, you cannot see my hand. Okay, if you focus on the linear region, that's basically very similar, right, to the variable resistor that we saw earlier, right? So different voltage, different gate voltage basically give you different resistance of your MOS transistor.
One question.
Mm-hmm.
So I get that like BGS sets like how many electrons are there in the channel,
Mm-hmm.
which limits the amount of current that we can get.
Mm-hmm.
But wouldn't increasing the drain voltage create more potential difference? And since electrons want to go to higher potential, wouldn't they become faster? And if they become faster, wouldn't the current increase? Why
Right.
does that not happen?
Right, so that's a linear region, right? With a higher drain to source voltage, the current is increasing here.
Yeah, but like if we keep on increasing
Mm-hmm.
the positive voltage at VD, why
Mm-hmm.
does it not like keeps on becoming faster and faster and faster?
Mm-hmm.
Is what
Right.
I'm
So,
saying. Even though the channel is limited.
right. I got your
Do you
questions.
get what I'm
So you're basically asking this saturation region, right? So why we discussed that if the drain to source voltage is actually greater to a certain value, the region is saturated. We'll not get to the detailed device physics actually in this class. 130 will cover more. But basically at a very high level, we talk about the drain, whenever the gate is on, we actually need to maintain a gate to source and also gate to drain. It need to be greater than the threshold voltage. If the drain, like here, the source is actually ground, right? So if the drain voltage is high and close to the, let's say it's also VDD and is the same as the gate voltage, there is no threshold voltage difference between the drain and the gate there. So in the CMOS transistor, if we have a picture, we don't have a picture here, but in the CMOS transistor, this is basically what they call this pinch off region. It's basically the channel actually doesn't exist. It barely exists. So the current can flow through, but the region actually close to the drain barely exists actually. So it's basically, you can think of it basically have a fixed width or fixed channel at that point. So after that, this is basically the minimum channel exists actually to keep the flow going, but that actually is not proportional to the voltage, to the drain to source voltage anymore for this region. So basically, you have a
channel size, it's the biggest closest to source, and it tapers off as we go closer and closer to the drain.
Exactly. Yeah, that's a really good analogy. You can think of that. Sometimes you also see people like draw a triangle there. Exactly what you said. It's actually wider as a source region because we can still maintain the drain to the gate to source threshold voltage, but very narrow at the drain to gate region. Yeah, you can think that way.
I see, that makes sense.
Good question. Yeah, so what Prashant asked earlier is basically the saturation region. Again, 3 regions completely off, less than threshold, linear region, right? Just like a resistor, nothing fancy, just like a resistor. And then saturation because it's actually, we cannot maintain the threshold. That's basically the 3 basic modes of our CMOS transistor. It's very similar to the topics, the resistance, actually very similar to the, like, I think some of you, like 16A or B actually should cover some of that. So anyway, no matter whether you have the background or not, but in this class, we are not going to go very deep this, but as conceptually thinking about MOS transistor, those are basically very important region of operation. So just a quick review, get more comfortable with the CMOS, the MOS transistor, how transistor works. I also want to just briefly talk about, we talked about the gates last time and also the design complementary CMOS gates, where we have the pull-up network. The pull-up network is always, we always use the PMOS transistors to actually make a connection between our output to VDD. So basically pulling the output to VDD. We also have our pull-down network. Pull-down network is always NMOS, right? So with NMOS, when NMOS is on, we basically pull down our output from output to actually to ground. So we'll have the output to be 0. So if you look at the pull-up and pull-down network, we basically always use pull-up network to produce VDD, to actually connect our output with VDD. And we always use pull-down network to actually connect our output with 0, to actually produce a 0. Just to link the topic a little bit more, some students also ask after the lecture, okay, we also talk about the good and bad 0. So the reason we use NMOS as a pull-down network to get the output to ground is because NMOS is really good at producing a very strong 0. And on the other hand, we always use PMOS to pull up our network, or pull up the output to actually produce a 1 or VDD. That is because our PMOS is really good at actually producing a very strong 1, right? So that's what we mean by good 1 or bad 1, good 0 or good 1. So the reason we use NMOS to do the pull down network, because NMOS is really good at producing a good 0. And on the other hand, PMOS is really good on producing a good 1. So we already covered that last time, but I want to make this connection, right? So the reason NMOS is used in pull down network, because we can actually fully discharge our capacitor all the way to 0, right? So in this case, I just go through this really quickly. We have an NMOS transistor here. Gate voltage is VDD. And then this is my output. So here I use a capacitor to represent my output, right? To pull down our output, is basically, in this context, basically discharging this capacitor, right? So at the very beginning, the voltage is VDD, and we want to pull it down so that the voltage get to 0. So in this case, we can actually pull this all the way down to produce a 0 here. But we cannot do that with PMOS here. The reason is to do that, let's try that. What if we actually want to also produce a 0 with PMOS? So in this case, the same setting, right? So we have a capacitor here. We also want to discharge this capacitor from VDD to 0. So with PMOS, my gate is on when when I have a low voltage here, right? So here I connect my gate to 0. So when I have a low voltage, my gate is on. So even the gate is on, my output voltage is basically my source voltage here, this node, right? Remember when we talk about whether my transistor is on or off, actually depends on the gate to source voltage. That need to be not 0. Remember the line where we drew the bottom line, the gate and the transistor is on actually when the gate to source voltage is actually greater than the threshold voltage. So the same here, this is our gate. Our gate to source voltage actually need to maintain our threshold voltage to actually keep the transistor on, right? So during the discharging process, and we are actually discharging our capacitors to the drain, from source to drain, because this is a PMOS. But in this case, we can actually not go all the way to 0 because we need to maintain the gate, or in PMOS, it should be source gate. The source gate voltage need to be greater than the threshold voltage. So at most, this node, the source node, the voltage is actually the threshold voltage, not a clean 0. We use 0 or 1, but it's really ground and VDD, right? But here, this voltage actually not as clean as this 0. It's actually pull all the way down to the ground. But here, we were only able to pull to the threshold voltage, which is actually greater than 0. So that's why NMOS is really good at producing 0, and PMOS is, if you have time, go through that exercise again to see why PMOS is actually good at producing 1. So with that, so go back to here. The reason the way we design CMOS circuit, it's always have 2 parts, and we always use NMOS to pull down to produce a strong 0, to actually really get a 0. But then we use PMOS to do pull up to actually produce a strong 1. So with this, we can actually get both a strong 0 and a strong 1. So we talked about the NAND gate last time to design a CMOS gates. Here, basically the pull down network is to find scenarios to actually producing 0, right? So if you look at the truth table, the pull down network should be on when both A and B are on. So if you look at the pull down network, A and B are basically in serial. Basically, when both A and B are on, both of them are true. My NMOS is actually, both the NMOS gates are on using our switch model. And then this is basically, we pull the output all the way to the ground. And we mentioned the pull up network is basically the dual version of the pull down network. So dual of the serial connection is basically parallel connection. So in the pull up network, so instead of doing the pull down to have 2 transistors in serial, we basically put them in parallel. So that's how we basically design a CMOS gate for the NAND gate. This is NOR gate, very similar. So one way, whenever we design a CMOS network, CMOS gate, always look at the output function, and basically the equations actually below the bar here is basically what we need to design in the NMOS, because those are actually pull 0, right? So basically before the bar applied, this is basically what we need to design in our pull down network, the NMOS part. And then after you design the NMOS, just do the dual of that. So if you have a parallel gate, and then in NMOS, and then we basically design a serial gate in our PMOS, right? So that's how we do the complementary part of NMOS and PMOS. So we have another gate here. Let's see, we have 3 input. In this case, we have A and B and the C. This is our pull down network. This is our pull up network, right? So what's the output here of X by looking at this pull down network? Well, so by looking at this CMOS gate, it's always easier to actually look at the pull down network just to see what's the functionality here. Any guesses? Let's see. So
it's not a NAND of A, B, and then ANDed with C.
Say that again, not a?
Like NAND of AB, and
NAND
then
of,
ANDed with C is what
so
I'm getting.
A and B, NAND,
Yes, and then all of this ANDed with C.
ANDed with C, and with C, this is what you mean?
Yeah.
Any other guesses? Let's see, we have a few. So let's see, like Android and JSON are, oh, Android and JSON are also different. Oh, GUI also have a different. So GUI1 is F is A plus B and C. We have, what other choices we have? F, oh, this, let's see, we have N choice is A plus B and C, and JSON also have then here, then A, do you mean AB here, Jason? And C, right? So let's start with this. So we have, let's put Prashant answer here, A, B, C, right? Oh, I'm so sorry, undo. Okay, good. So as I said, I actually always like to look at the NMOS. That's actually a lot easier. And we mentioned earlier, so it's always the inverse, right? So whenever we look at the NMOS part, we always map at a bar here. So with that, we see we have A and B in parallel, right? We look at from bottom up. So we have A and B in parallel. In parallel means an OR relationship. And then we have C in serial, and C means an AND relationship, right? And then we have this bar here. So let's see who got this right. So this one is right. This one, okay, so I think Gia and Troy have the same answer. So Jason put A and B. Just look, like we look at the NMOS part, right? So A and B are in parallel. Parallel means OR, right? So that's what we have here. So this is basically how we can actually look at any arbitrary gate. Always start from the NMOS part. NMOS, you can actually just write the function directly and then add a bar because it's actually pulling down all the way to 0. And then we keep doing this. The reverse part, A and B is actually in parallel. Now in drawing PMOS, we put A and B in serial. And then we work with C was in serial with NMOS. And then when we do PMOS, remember it's always a dual of that. So we put B in parallel. So with that, this is basically our function. Let me clear this. And sometimes if you look at this function, this basically we do an OR gate first, and then we have an AND gate next, and then we have this bubble here, which is an inverter next, right? So sometimes you see people actually call this is OAI gate because this is doing OR and inverter. So this is basically how we can actually, we talk about how we do truth table to Boolean algebra, and also you can actually also map to circuit. Well, of course, there are different ways to map a circuit, but when we design CMOS gate, this is basically how we either turn a CMOS gate into a Boolean equation, or we can later to turn this into a truth table, or the other way around, start from truth table, get to the Boolean equation, and then design CMOS for it. So now we see the full picture, right? At the very beginning, we see if you remember the 3 triangles we saw before, like truth table, Boolean equations, and then like gate circuit. So now we see how they can actually change with each other, how we can actually take the equation to get the circuit, or take the gate circuit and to derive the Boolean equation here.
I have questions.
Mm-hmm.
So if you go back to that slides, so the way I understand this circuit is basically if we wanted to get VDD, that means A, B has we have 2 paths. One path is through A, B, and the other path through C, right? So either like A and B together has to be not, or C is be not. So what I had is just like not A times not B plus not C. I think it's going to be same logic at the end, but I don't know if this way is the
right. Your understanding is correct. So you either need to actually pull both A and B up. Always remember there's a this is inverted switch, right? So there are two parallel paths. You can always pull that up with one loop path. If you have time, you can also do this with the Morgan theorem. That will actually also get you to the right equation.
Yes. I think that way we'll also get the same expression, but like just like I think my question is like, do we always want that to be a big bar at the top, or I guess that's my questions.
I see. So you will design NMOS first, right? Then we like to have a big bar at the top because we actually design NMOS, right? We design NMOS, and then this is how things connected. And when the bottom equation is true, we are actually getting a 0, right? So if the bottom part is true, we actually, if this part is true, x is true, sorry, x is actually 0. So if we actually design in the way we start from NMOS, like the exercise I went through, we always do a bar here. But if you change this, you can also keep applying the Morgan theorem. You could also actually get the PMOS version. That could be a different way to do this. Okay, so a little bit more review of the CMOS MOS transistor behavior, and we also talk a little bit more in more details about how we can actually build complex CMOS gates, either from Boolean equations to gates or from gates to Boolean equations. So next we're actually going to talk a little bit more. We talk about, if you remember early on, we talked about design metrics, right? So we talk about the power, performance, and also robustness, and also the cost. So back then, when we talk about performance, we talk about the delay part, right? And we really need to consider the delay that play a really important role when we design hardware. So in the next couple of lectures, we're actually going to take a look at what kind of factors actually contribute to the delay of our circuit, especially when we think about the transistors that we have and how they actually affect the delay of either a single gate or a longer chain of gates actually connected together. So with that, we'll briefly talk about the delay and why we care, what are the different implications. We'll use inverters as a good example to talk about different factors that contribute to the delay. If you have time, we'll talk about the sizes. If not, we'll actually talk about that in the next lecture, next week. So whenever I talk about delay, a more direct metric, especially when we think about today's hardware performance, is actually frequency, right? So whenever we buy processors, we always look at what's the frequency the processor is actually running at. So if you look at the past 4 decades, actually generations of microprocessors actually built from major hardware vendors. If you look at the transistor, so this is actually mid-2011, right, roughly 5 years ago. If you look at the transistors, which is the top, right, the top brown-ish triangle here, right? So we have been more or less actually following Moore's law pretty consistently by providing more transistors over a year, right? We always have more transistors to use. And one thing we do notice that if we look at both single thread performance and also frequency, especially frequency, when we look at the green box here, if you look at the frequency at the very beginning, the frequency also track with a Moore's law scaling pretty closely, right? So when we have smaller transistors, we'll have more transistors. We actually also get a faster processor. Our processor can run at much higher frequency every generation. With that also translates to a lot of what we call single thread performance, right? That's highly related to the frequency of the processor that's running. One thing we did notice, even we mentioned like over this period, it seemed like the Moore's law is still going. We have more transistors here. But one thing we did notice that around mid-2000, even early 2000, right, the frequency actually started plateaued. If we look at over a year, right, we do enjoy this growth in most of the time, but then in the recent 10 or 20 years, the frequency is more or less plateaued. Even the transistor is actually indeed smaller, we cannot while the transistor generation say they are actually also smaller, we can actually not get higher frequency of our hardware. One thing that's actually related is the reason why we are actually plateaued here in terms of frequency is also related to the processor, the power of our processor. We also notice that our processor, the power consumption is actually, we're at the 100 watts, 100 watts region for our processors already. And that actually significant limit that achievable frequency that we can achieve. We talk about Moore's law and linear scaling, how that actually affect the transistor behaviors. We'll not talk too much about that, but it's really interesting. You will look at the history of the data to see how frequency was actually increasing, but then actually later plateaued in more recent generation. And coincidentally, this is also when we start actually increasing, having more cores in our hardware, because it's really hard to actually get higher frequency and also provide higher single thread performance. One alternative that designer choose, hardware vendors choose, is to actually by provision more cores to have more thread level parallelism to deliver higher performance. And then more recent, the trend is not only just multi-cores, but also start introducing even more specialized accelerator. So all those workarounds in some sense is really trying to still provide performance growth, but without relying on frequency increase. So why it's so hard to increase frequency? What are the different factors that we need to be aware? So if you think about frequency, that's basically related to the delay, right? That's basically the inverse of the delay. If you think about delay operation, we talked about the critical path earlier. That actually critical path really important when we think about the frequency or the achieved frequency, or basically the speed that we can run in our system. When we think about optimization, I think we also discussed earlier when we talk about architectural level, like pipelining is a good way to actually think about delay optimization to actually have more pipeline stage. So each stage is actually shorter, and then you could have higher frequencies there. We'll also talk about logic level, what kind of, we'll actually see more later when we get to like some of the more building blocks, especially for example, adder and multiplier with different ways actually structuring your adder and multiplier. You could also get to different critical paths and have different delays there. At the circuit level, one important trick that we'll be discussing likely next week is how we can actually, we talk about the size of the transistor, right? How that actually affect the resistance of the transistor, and we'll also see later it will also affect the capacitance of the transistor. How we can actually play with or modulate the size of the transistors to actually deliver a better timing or improved performance here. So in today's lecture, we'll actually model the delay or model the transistor as a very simple RC circuit to actually provide some interaction in thinking about the delay at the transistor or at the circuit level, how the different factors that contribute to the delay of our circuit and what kind of optimizations we can potentially do at individual transistor level. We'll talk about more about transistor sizing next lecture. We'll talk about that's also an important way to change the delay to perform delay optimization. And also instead of focusing on the inverters, we'll also generalize to other circuit building blocks. So with that, we'll be focusing on the inverter delay for the rest of the lecture before we get to more general delay optimization. So on the logistics side, not a lot of new things. New lab, we have our final lab, lab 6 this week. So this will be our last lab. So definitely use this lab, use this week as an opportunity to wrap up your lab, and we'll start project next week. So the project spec will be released next week. That officially start the second part of this class. We'll transition from the lab mode to the project mode. Homework 5 will be due tomorrow. This is a 2-week homework that was out 2 weeks ago. So hopefully you already have enough time working on it. It's due tomorrow, and we'll have a new homework due today. It's a lighter homework for this week, since it's right after midterm, and not a lot of new material introduced, so it should be a light homework. But again, get started early is a good way. After today's lecture, you should have all the information for this homework. So get started early and use this homework as a good opportunity to get more familiar and comfortable with the topic. We'll have a guest lecture. I mentioned we'll have 2 guest lectures, the way I structure those guest lectures, really thinking of like what kind of topics that are, unfortunately, we don't have time to cover, but will also be useful in your future career, especially during your interview process. So we'll have the first guest lecture next Tuesday. We will be talking about, we talk about the design, different design metrics, different ways of building the design. We'll see actually more later this month, but it's really good to see as a hardware designer, especially as a system architect, how we actually balance different constraints or different metrics in the design process. So Jared, many of you have seen him already in the Apple Berkeley new initiative announcement. So he will be here both interacting with the students and also talk about some of the more practical SoC design experience in their design process. I'm still trying to figure out whether it can be recorded or not. So I would strongly recommend all of you actually join this live. It's not only just the lecture itself, but also interacting with the guest speaker. So next Tuesday, our lecture time, we'll have our first guest lecture, and then we'll have another guest lecture early in November, focusing on verification. So that's the logistics side. Any questions, comments before we move on to inverter delay? Okay, so well, in some sense, inverter is our favorite circuit at this point. All of you should be actually pretty comfortable actually looking at inverter here, right? Even when we talk about a logic gate, we started with inverter. So with this inverter, basically we have the input signal goes through our inverter gate, and then the output is actually the inverted value of our input. So from 0 to 1 or 1 to 0. We talk about how we can actually abstract our transistors as basically a switch with a resistor here, right? So here, once we start talking about delay, instead of looking at this abstract gate, we basically decompose that and use our switch model to represent both our PMOS transistor and NMOS transistor, right? So an inverter basically a PMOS and NMOS, right? NMOS actually do the pull down part, PMOS do the pull up part, and the same input is being applied to our switch or to the gate to actually either turn on or turn off the switch. So here is our switch model for our inverters. We have 2 switches and also the resistance, using this resistor to represent the resistance of our PMOS and also resistance of our NMOS. So here, when we talk about delay, we always also, the output of the delay will be actually driving either another gate or some other circuit function. It could be either an inverter or some other gate. Right, so whenever we talk about output, we actually also consider the load capacitance here. So load capacitance basically is the capacitance of the load itself. At the same time, we also talk about, we'll get to that, or maybe we'll talk about either today or next time, but whenever we think about transistors, there's also parasitic capacitance here that actually associated with the transistor itself. So we think about the capacitance actually affecting the output is both a combination of both the load capacitance, things are actually happening after my output, and also my parasitic capacitance, things happening actually in my gate. We will not talk, no need to worry about that. We'll just combine them together. Basically, both 2 factors actually affect the output capacitance here. So when we think about delay here, let's see. We are interested in the delay of doing a high to low transition. We talk about propagation delay early on, right? So propagation delay, 50% to 50%. And there are 2 parts, either a low to high transition or a high to low transition, right? For our propagation delay. So let's start from our high to low transition. So if my output actually go high to low, this is an inverter, right? So if my input is actually go from 0 to 1, right? This is over time. This is over time. So if my input is actually going 0 to 1 over time, so my input is actually 0 to 1, and then my output will actually go from VDD to 0. So this will be a high to low transition. So in this case, once the input is actually get to VDD at the time 0, my NMOS here is turned on, right? It's connected. My PMOS here is turned off. So we'll basically just use this equivalent circuit here where NMOS is turned on. So we have the resistance from my NMOS transistors and then capacitance from both my load and also my parasitic capacitance of my my transistor. So now this is basically very familiar, the RC circuit that we have hopefully, no worry about RC circuit if you haven't seen that before, but basically we have a very simple circuit with both resistance and also capacitance that actually in my circuit. And the time from our high to low transition is basically the time it takes to basically discharge our circuit, right? So once my before time 0, my output is high, right? That's VDD. So my capacitance here actually have some storage, right? Some have charge actually stored in my capacitor. And then once my NMOS is turned on, I basically have a pass through the resistor. I have pass to connect my capacitor to ground. And then I start the discharging process as my charges actually move from my capacitors all the way to ground. So, and then eventually when the capacitor is fully discharged, my output voltage is become 0, right? So when we think about the delay, so if we think about the behavior of our output also over T, right? So at the very beginning we mentioned, right? So it's a 0 to 1. So before, at the very beginning, when my input is low, my output is high, right? So at the very beginning, when my input is low, my output is high. And then my input, when my input becomes high, it becomes an inverter. So this inverter turned on, we get this circuit here. I start discharging, my capacitors start discharging. And then after a while, it will become 0, right? So this is a high to low transition that we talk about here. So if you look at the circuit, there's no reason to remember any equations again in the behavior, but if you think about the way my voltage actually change over time, this is basically an exponential decay function that can be represented here. Again, no need to remember the equations here. If you're interested, you can actually analyze this RC circuit at very high level. Basically, once you first start discharging, right? So at the very beginning, my output is VDD. So if you look at, we talked about the Ohm's law earlier, right? So you look at the current actually flowing through my resistors. It's actually basically VDD divided by resistor. That's basically the highest current that I can achieve, right? And then over time, I start discharging, and the node here, the voltage is actually going down. So at the very beginning, I discharge really quickly because I have a high current. And then over time, when my voltage is actually going down, my current is also going down. So I start discharging a little bit slowly. So this is basically this exponential decay curve that we're observing. Again, no need to remember anything, just see we are starting from VDD and getting to 0, and I charge a lot faster at the beginning, and my discharging a lot faster at the beginning, and things start slowing down when my output voltage is also getting low, right? So this is basically the behavior. When we talk about circuit, it doesn't just transition in one shot, right? So it actually takes time. We have the capacitor here. It actually takes time to actually discharge our charges on our capacitors. So that's basically what is actually behaving here. So in this case, we talk about the propagation delay, right? So it's basically 50% input, 50% input to the 50% output, right? So this, the time it takes here is basically our propagation delay, right? So we talk about this is basically an RC circuit. R is here, the resistance of our NMOS, and C is basically the capacitance here. Let's just group them together. No need to worry too much about this. Just assume this is the capacitance of this output capacitor here. So with an RC circuit, it basically the delay here to reach 50% of VDD is basically ln 2, or basically 0.7 of a time constant. The time constant is basically the resistance exists in our circuit times the capacitance that exists in our circuit. And then the time to actually discharge the circuit to get to half our capacitance is basically 0.7 of this time constant. So this time constant only associates with the resistance of the circuit and also the capacitance of the circuit. Again, no need to, this is basically the time constant in the equation. No need to remember the equation at a very high level, right? So why the time constant is this? So if we have, let's say we have a higher resistance here, right? So this resistance is higher. We talk about the current is basically the voltage divided by the resistance, right? So once we have a higher resistance, my current is lower, so it takes longer to actually do the discharging, right? We need to actually move the current to move the charge, which is actually the rate of moving the charge is the current, right? So if my current is actually, if the resistance is higher, current is lower, it takes longer to actually discharge. So that's why this is resistance here. And similarly, if I have a bigger capacitor, I'm actually storing more charges there. It also takes longer to actually discharge my circuit. So the time it takes to charge and discharge my circuit is basically related to both the resistance exists in my circuit and also the capacitance exists in my circuit. If you have time, you can look into the equations, and there's also, you can use differential equation to actually solve this. No need to do that, but very intuitively, this is basically the curve of how output actually change over time. And this is a propagation delay that we mentioned earlier, either low to high or high to low. So here we're focusing on the low to high propagation delay is basically 0.7 of our RC constant here, resistance of our capacitance constant here. So that's basically our inverter delay. So we talk about it doesn't just happen immediately, and the time it actually takes to make the switch is actually related to the capacitance and also resistance that exist in this circuit. So we talk about high to low delay. Similarly, there's also the low to high transition. So when input start with high and then transition to low, right? So if the input is low, similarly, the equivalent circuit is basically my PMOS starts on, right? So if PMOS is on, when input is low, and then my NMOS is off. So here, instead of the discharging circuit that we saw earlier, we have this charging circuit that we actually charge our capacitors and capacitor from zero to VDD, right? So this is basically our low to high transition, right? So we talk about high to low, propagation delay has both low to high and high to low, right? So here we talk about the low to high part is with basically PMOS. And then the same, it's also an RC circuit. It also is basically the time constant only related to the resistance exists in the circuit, and also capacitance exists in the circuit with 0.7 because we're looking at reaching half of the VDD. Right, so when we think about delay before, it's fairly abstract. We just say, oh, it takes time. So now you see why it takes time, right? Because we actually need to charge and discharge those capacitors to actually reach the target output voltage, and all of those transitions actually takes time, and the time it takes basically related to the resistance in our circuit and also capacitance in our circuit. So here we talk about the inverter delay, both low to high and high to low, right? So one thing here, like we have been using this is some extra information, no need to worry about it, just for your information. Like some folks may already wondering, okay, you tell me that I can just use basically a simple resistor here to represent the resistance of our NMOS in this case, right? But earlier you also told me some region of my behavior, one part linear, that's a fixed resistor, but in the saturation region, that's more like a variable resistance because that's actually with different voltage here. So in general, there are also fairly complex equations. No need to derive those equations to actually think how to get what we call like equivalence resistance. So instead modeling this as a variable resistance of modeling our NMOS as a variable resistance, we could actually just using a single value to represent the resistance of our NMOS. So what we do here, we just have what we call, you may always see we have this equivalence resistance. Earlier, we will talk about NMOS and PMOS. So here, basically, as a very rough approximation, we basically say we start from here and halfway here for our VDD, and then we just do the average resistance, which actually happened to be a fairly close, actually, approximation to for the equivalent resistance of our circuit. So here, from now on, we see NMOS transistors, understanding there are nonlinear behaviors in the NMOS, in our MOS transistor, but we always just use this equivalence resistance to characterize the overall resistance of our circuit. So here, no need to worry about it's actually changing. We just have this equivalent resistance, and that can actually be approximated by the starting point and also the ending or the halfway point of our circuit here. So we talk about the high to low and low to high transitions. We'll talk about some of the different factors. Oh, let me clean that could actually affect the behavior. So one of the first things we mentioned earlier, we have been talking about for the, this is high to low transition, right? My input go from low to high, right? Before, we have been assuming my input just go to high at time 0, right? So that's our old assumption, right? But that's also too ideal. Not only like we talk about is actually every transaction actually takes time, right? So instead it has that ideal view of our input voltage here. It also actually takes time for my input voltage to actually go up, right? So it's not just like a very clean step function. I just go all the way up. It actually takes time to go up. You remember if I use red to represent the old scenario where we have a clear transaction here, right? 0 to 1 transaction, and then with transition, and then we say our current is basically have this behavior to actually start with very high and then start going low, right? But then more realistically, if I can. Okay, so this is updated here, right? So it actually also takes time for my input to transition from low to high, right? So in this case, when my input actually transition from low to high, it's basically, remember the input voltage is basically the gate voltage, right? So remember our very simple behavior, we talk about how this basic different lines here, it's basically different gate voltage that actually apply to our transistor. We just reviewed that a minute ago, right? So with different gate voltage, I actually have different current actually associated with the gate voltage. If my gate voltage is actually low, I cannot reach a very high current because that's actually also limited by my gate voltage. So more realistically, if you think about the transition, it takes time for my input current to actually go up because my gate voltage is gradually going up, right? Gate voltage is basically the input voltage here. So this takes time. So my input voltage current takes time to grow. And then I start the decay process. So my current actually start taking more time actually to get to, even to reach this highest current point, it actually takes more time. So if we think about my voltage transfer characteristics, right? So we say this is basically doing a discharging at a high current. I can actually discharge really quickly, right? But in a more realistic scenario, when we actually consider it also takes time for the input to transition. So with that, it's actually slower. It's actually slower for my output to reach the low volt. It's actually discharging a little bit slower because my current is also lower here. So once we actually, so we say this is original latency or propagation latency from high to low transition. Once we actually also consider the time it takes to do the rising for the input to transition from low to high, the circuit is actually will be even slower. So that's what we do. We show here. So we talk about inverter delay, but when we actually realistically consider the input, it also takes time for input to transition. So our circuit will actually be slower. It actually takes longer to reach half of the VDD point. So a quick exercise. We have been talking about this for so long. So let's do a quick exercise here. We talk about inverter delay, right? So I just went through an example to show how my input transition, the delay in my input transition could also impact my inverter transition propagation delay, right? So in the same example we have been running here, when we're actually doing the discharging, right? We're doing the high to low transition here. So what if my load, so we talk about the load capacitance, we'll see actually more. You can basically think about all the gates. Gates don't, like circuit don't exist on its own, right? We have this circuit, it's actually need to drive another circuit, right? So this is our load capacitance. Basically, you can think about the capacitance of all the circuits that I'm driving, right? So what if my load capacitance actually double? So if my load capacitance actually double, so we have a bigger capacitor in this RC model, we have a much bigger capacitor here, right? So if this is blue, it's basically the original V out curve transition. What is the correct the V out transition over time for the new circuit where our load capacitance is actually doubled? So you have a bigger load that we need to drive. The CL is actually bigger, which is the right V out transition behavior. Is that actually faster? Let me back to yellow. Is that actually faster or the same, or is actually slower? The yellow key is speak. Speak up, everyone. So how would my circuit behave if I have a bigger, oh, can you actually still see my, okay. If I have a bigger load capacitance. Oh, it doesn't work. 1 second. Oh, my apologies. Try this one. Does the full link work? Okay, well, thanks, Vikram, thanks, Jingyue. Yeah, think about it. So we talk about is this RC circuit, the delay, right? Different factors. So we're mostly talking about the internal factors of our gate, right? So, but what if I'm actually driving a much bigger load? I have a much bigger load capacitance. How is my circuit going faster or slower in this scenario? Okay, think about it. Let's do 1 more minute.
Are we still assuming ideal case of like this V in transition?
Yeah, let's still assume this ideal case. Yeah, what I had here, right? So this is a baseline. Yeah. Yeah, let's do isolated. So it's still ideal case. So this is our base, and the blue is basically the baseline. The only thing changed is that I'm driving a much bigger load. I actually have a more complex circuit after me. It's a lot harder to drive with a higher capacitance. How would that behave? Okay, 20 more seconds. Okay, we have more than 20 responses. So let's see. I think most of the students say is C. It is actually slower. Yes, the right answer is C. I think most of the students get it right. More than 80% of students get it right. Good job, everyone. Right. So we mentioned this is an RC circuit, right? The time constant is basically RC together, right? So with a higher load capacitance, we basically have a higher C. So our time constant is actually longer. So with a higher time constant, our circuit is actually slower. I mean, there's no need to remember like RC circuit, the original exponential decay function. Just imagine, like we talk about R, right? We already talked about it with a bigger resistor, the current is actually smaller for the same voltage, right? So it actually takes longer to either charge or discharge. And similarly, with a bigger C, with a bigger capacitance, you have actually more charges stored in your capacitor. With that, it also takes actually longer to both charge and discharge your capacitors. So we'll see later when we talk about when we chain multiple gates together, the load capacitance is actually a very important factor. Depends on the load you're driving, you may actually size your transistors differently because you want to optimize the RC delay of your circuit. So with that, yeah, we'll not get to the inverter, we'll not rush it. It takes time to review this. We'll just stop at the RC delay here, just how the CMOS, in today's lecture, we capture how we have a quick review of how the CMOS transistor works. Again, 3 regions, very, very simple. Less than the threshold voltage, 0, nothing going on. Greater than threshold voltage, basically just a resistor, linear function. But then if your drain voltage is too high, it becomes saturated, so you get this flat region. So that's basically the 3 modes of our transistors. We'll also talk about how we can actually use pull up and pull down network to build complex gates. And then we get to the delay discussion, how we can actually optimize delay to improve the frequency of our circuit. And we never talk about delay. Whenever we think about circuit delay of a specifically an individual gate in our current discussion focusing on the inverter, it's basically a very simple RC circuit. Again, no need to remember the equations. No need to do any, like sometimes people do differential equations to solve this problem. No need to do that. Just see how graphically how input and output change and what are the different factors that affect that. We already hint a little bit, right? In the last exercise, load capacitance actually really matters. And we also need to actually size our, like both resistance and capacitance really matters for the delay. We actually want to size our transistors actually differently based on different delay requirement. We'll cover more about delay and how we size transistors next week. So good to see you all. Have a good weekend and take care of yourself. Remember next week Tuesday we'll have a guest lecture, and then we'll continue our discussion on the delay for our Thursday lecture. So good to see everyone. Take care and see you next week.
I have